I'm really pleased to introduce our speaker, Dr. Steve Royce. Steve is a software development manager at ANSYS, a leading global provider of engineering simulation software. Steve has over 15 years of experience in software development and management, and he currently leads a production creation team responsible for delivering simulation solutions. So please welcome Steve.
Thanks very much, Elaine. Thank you all very much for joining me today. What I hope to do is to shed a little bit of light on how simulation is really an integral part of moving forward with autonomous vehicles. Autonomous vehicles are starting to show up a lot in the news. I was very lucky last night to stumble upon an article from the CBC highlighting a local autonomous vehicle, the Autonomous, which is run out of the University of Waterloo. And really the commitment and ongoing commitment from the Ontario government to let autonomous vehicles drive on Ontario streets to help further their development. What I'd like to do, as I mentioned, is to talk a little bit about simulation and how simulation is a big, big part of designing autonomous vehicles. If there's anything you walk away with today, it's these four numbers. 585,000 is the number of lives that are predicted to be saved between the years 2035 and 2045 when autonomous vehicles are believed to become mainstream. 8 billion is the number of miles of testing that we think are needed in order to ensure or convince ourselves that autonomous vehicles are just as safe or safer than human drivers. 400 is the number of years it would take to have a fleet of about 100 vehicles running 24 hours a day, 365 days a year. It would take 400 years to cover that amount of testing by doing road testing with these vehicles. 10 years is what it's going to take to pull this off with simulation. Whether we want to admit it or not, there's a revolution happening. And by revolution, I mean that in the most honest way. Autonomous vehicles are poised to change what we do, how we do, sometimes even why we do what we do as far as traveling around. Certainly, we're aiming to have self-driving cars and robot taxis, but drones are already flying around. And for those of you who have drones, if you're lucky enough, you might have a drone that has a come back home button. And that's quite autonomous. You can have flown your drone somewhere else and hit that button, and it'll fly back and land at your feet. Autonomous and mobile robots are also quite pervasive in the industrial setting. We've got 2 robots vacuuming our house probably right now to clean up after the dog and the kids. So they are, this is not something that is way off in the future. This technology is already a part of our lives today. I mentioned at the beginning some of the numbers that are relevant. I want to take a step back to that and really ask the question, why are we as humans so profoundly motivated to pursue autonomous vehicles? And the answer is because they're going to have an amazing effect, a profound effect on our lives. There's a prediction of drastic reduction in fatalities associated with automobile accidents. I mentioned this number, 585,000 lives per year by the 585,000 lives saved in that period. In fact, today, 1.2 million people a year are killed in automobile accidents. So it's a very significant number of people that are killed due to automobile accidents. And if we even have a fractional change on that, it can be very beneficial to us. There's a tremendous economic impact that we expect to see. Numbers that we got out of a report published by Intel show that they're expecting by the year 2050 to see about a $7 trillion economic impact annually. That's a massive economic impact that spans not just our own personal use of autonomous vehicles, but autonomous vehicles in the business context as well. There are a large number of people that are not mobile, that are not able to get around. Autonomous vehicles are poised to have a profound effect on them as well. So quality of life, quality of living is also set to change and improve because of autonomous vehicles. And then finally, if you travel in and out of some of the major cities in the world, I'm sure you've been frustrated by the amount of traffic that's there and the amount of congestion that's there. Autonomous vehicles are also poised to have a profound effect in that context. If you think about it, there are hundreds of millions of hours spent commuting, sitting in traffic all the time. And those hours, that time can be freed up to do more productive things with the introduction and widespread use of autonomous vehicles. One of the things that I came upon as I was researching autonomous vehicles for this presentation is what I would suggest is this path to autonomous vehicles, the 5 levels of autonomy. Today, most of our cars are several years old, and really they're driver only. And by this, really what it means is that if you're lucky, the turn signal will turn off when you finish your turn, right? That's the extent of automation that we get today. There are a number of newer cars that introduce what's considered level 1 automation. Level 1 automation is something like the adaptive cruise control. The big thing here is that there's a sensor on the front of the car which is monitoring the vehicle in front, and it will keep the target speed that we've set, but it'll also keep the distance between us and the car in front. Okay, so that's an example of an advanced driver assistance system, an ADAS system, which gets us to level 1 automation. Level 2 comes from mixing multiple ADAS technologies. So for example, if we take the adaptive cruise control, and to that we add something like lane keeping technology, which is watching beside the vehicle to make sure that we stay in the center. And as the road turns, it's going to help us to turn. If we tend to one side of the lane or the other side of the lane, it'll push back a little bit. So here we're starting to be able to relax a little bit as a driver and maybe not have to get as tired, especially for long drives, in keeping track of what's going on the road. Level 3 is what a lot of people would consider as conditional automation. Now we're starting to see steering, acceleration, deceleration, all tied into, for example, the navigation system. The vehicle itself can make decisions about when it gets on and off the highway, maybe if it needs to pass because you're behind somebody who's going a lot slower than it thinks you should be going. The word conditional is there, however, because it would be limited to certain kinds of roadways with certain maximum speeds, etc. Once we get into high automation, or level 4, we start to see pretty much a fully autonomous vehicle, except that a driver still needs to be there, because that autonomous vehicle will be monitoring what's going on around it and in it, and if something odd happens, if there's an exception, it'll signal the driver, hey, you've got to take over. So the driver still needs to be there, but to a large extent, they can sit back and really relax and enjoy the ride. Full automation with no driver is what I'm really going to be talking about today, okay? What do we need to do to get to this point? At this point, really, you could imagine having a coffee table in the middle of the car with 4 very comfortable seats, no driver. You say, I want to go to Toronto, and get in the car and you wait, and when you get there, you get out. What do we need to do to make this a reality? To make it a reality that we don't need a driver in the vehicle? Well, what we need to do is understand what the driver does, all right? And the observation to be made here is that certainly there's an environment in which the autonomous vehicle is driving. That's a really important piece of the puzzle. Then we get into a driver control loop. That driver control loop contains 3 main pieces. One related to perception. The autonomous vehicle needs to be able to assess what's going on around itself. The next main component is motion planning. So the vehicle needs to assess what's going on and decide what to do. And the last thing is that it needs to execute whatever it wants in terms of motion with the various systems in the vehicle. So the equivalent of what you guys would do is you decide you want to go off the highway. based on perceiving that the lane is coming up and you can go off the highway. You decide you want to go off the highway, then you turn the steering wheel, take your foot off the gas, maybe you have to brake. That's the motion execution part. It's that last stage. Obviously, our vehicles need to change pretty substantially in order to pull this off. And there are two main changes that will take place. The first one is the introduction of a lot of new hardware. We have LiDAR and Radar. LiDAR is laser or light-based detection and ranging technology. And essentially what this technology is doing is it's sensing the existence of various objects, and by processing that signal, it's able to figure out, is it coming towards me, is it going away, etc. Radar is a complementary system in that it provides another way of observing roughly the same kinds of things. In this case, it's not using light or lasers, it's using radio signals. Both of those are bouncing signals off of various things in the surroundings and reading the signals that come back. Simply knowing that there's an object in front of you is a great thing to make sure you don't hit it. But as these autonomous vehicles are driving around in the environment, they're going to need to be able to assess what color the various traffic lights are. They'll need to read the signs that we see and read every day. Is this a one-way street? Is this a right turn only lane, etc.? That's where cameras come into play. That's where cameras become a really important piece of the puzzle to augment the detection and ranging technology. The last hardware system that I'm going to talk about today, and of course there are others, but I'll focus on these three, is all of the electronics that are needed to integrate all of this into the overall autonomous vehicle package. Of course, once we add the hardware, we need software to control it and interact with it and present what's going on to the user and couple the various systems inside of the vehicle itself. For the perception part, once the signals have been perceived and taken in, there's a lot of software that goes into processing those signals. What I mean by this is deciding when we see an image of something, is it a truck? Is it a car? Is it a tree? Is it a pedestrian? In the motion planning stage, there are three pieces that I want to highlight in terms of the software and what the software has to deliver. The first, and probably the most important, is making control decisions, right? This is deciding, do I go off the highway, or if there's the potential for a collision to occur, well, what am I going to do to avoid it? A lot of information needs to get relayed to the passengers that are inside of the vehicle. And the last thing that the control system needs to do is, knowing what needs to happen in terms of the motion, it's got to generate the actuator inputs, the inputs to the motion system itself. The motion system and executing the motion that came out of motion planning is really down to the vehicle and vehicle component dynamics. All right, so there's software that's related to having the vehicle understand how it itself is going to respond to various inputs. I'd be remiss if I didn't mention artificial intelligence as well. So deep learning is an absolutely critical part of both signal processing and the control decision process as well. The thing to understand here is that it doesn't matter how many possible combinations that we as software developers could come up with for recognizing a car or a truck or a tree or a pedestrian or deciding what to do in different conditions. We can't possibly conceive of all of the scenarios that could come up. And that's where something like deep learning really comes to be an essential piece of the puzzle. Right? That's helping very much to round out all of the different scenarios that could happen and then take place. I've introduced in the last two slides two major sets of changes that need to take place. And it's conceivable that these things aren't going to work perfectly, especially when we integrate them all together right out of the gate. So there's no question that a lot of time needs to be spent thinking about how do we demonstrate the safety of these new autonomous vehicles. In fact, that is absolutely the most critical thing. The technology, we can work on that, but widespread adoption is absolutely contingent upon us demonstrating that these autonomous vehicles are actually safe. Rand Corporation a few years ago took a step back and they tried to answer the question, how much testing is enough? And so they looked at it and they posed the question, how many miles of driving is actually required in order to pull this off? Of course, you know the answer. They determined that it would take about 8 billion miles of road testing to validate autonomous vehicles over the millions of scenarios that could exist in the environment that these vehicles drive in. If we were to actually have that fleet and do the actual driving, we would have to equal the 8 billion miles that need to be traveled. We would have to travel every single road, every dirt road, every driveway, every paved road, every highway. We'd have to do that in every city, every province, every country, every continent, 200 times. That's the amount of testing that we figure would be needed in order to pull this off. So it's an immense, an absolutely immense amount of testing. And you know, having a reasonably sized fleet of vehicles doing this 24/7, the idea came up earlier. It's 400 years to pull it off. It's a very, very long time, and we won't wait for that. We can't wait for that. So the bottom line is, road testing by itself, it isn't a solution to solving this critical challenge. So how can we do that? How can we prove to ourselves that autonomous vehicles are indeed safe for widespread use? I only needed to Google it, and by that I mean Alphabet, which is a parent company of Google, and Waymo has been testing autonomous vehicles for some time now. Waymo is the subsidiary of Alphabet that's doing that. They started about a decade ago, and ending in the middle of last year, they had their real vehicles driving on real cars, and they had covered 8 million road miles. That's 1,000 times short in those 9 years. That's 1,000 times short of the 8 billion that we figure are needed. They saw that, of course, and they said, you know what, let's come up with virtual cars in virtual environments, and let's try to simulate this. Let's try to use simulation to cover the ground that we need to in terms of the testing. So, you know what, they are able to simulate. They've simulated 8 million miles. They didn't do that in 9 years or 1 year or 1 month or 1 week. They did it in 1 day. They do it every single day through simulation, another 8 million miles. And if you do the math, that ends up being about 2.5 billion miles per year. That puts us in that striking distance of having viable autonomous vehicles in about a decade. It confirms also that simulation is absolutely the only way that's practical to validate autonomous vehicles over the millions of scenarios that need to be tested. Begs the question then, what does this simulation actually look like, right? It's not really taking the car and drawing a grid on it, right? There's a lot more to it. So what does that actually look like? This is autonomous vehicle testing software, simulation software. On the left-hand side, we see the environment. Okay, this is the environment that the autonomous vehicle, the simulated autonomous vehicle, is going to be driven in. There's a road plan, we see the environment, we see the vehicle in front, vehicles in front, there are street lights, there are buildings around it, because that's truly what the environment looks like. These vehicles are driving in environments like that. In the middle right, we see some feedback regarding the perception, the sensors. Okay, so this would, for example, be some of the feedback that was obtained from the LiDAR system or the radar system, and then signal processed and shown here. In the bottom right, we get into the control system, the motion planning. The motion planning for the simulation that I'm about to show you has two parts. It's got an adaptive cruise control, and that's going to keep us, it'll set a speed, and it'll keep us a certain distance from the car in front of us. And the second piece is to avoid obstacles, and we'll see an obstacle run out in front partway through the simulation. The last thing to note, and I mentioned it earlier, part of the software that's involved is relaying what's going on to the passengers, no longer drivers, to the passengers inside of the vehicle, And so this then is an integral part of the actual simulation as well. So here's the simulation. We see the vehicle in front. That's that gray vehicle. We're keeping our distance in a cruise control mode. Now that vehicle will perhaps slow down and decide that it wants to turn. We're keeping our distance from it. And as it moves out of the way, we want to accelerate, but this pedestrian half runs, half walks out in front of us. I'm not quite sure what to call it, sort of like a reverse moonwalk or something, but the pedestrian's out of the way, and we re-accelerate, and you can see here the speed of travel is not constrained by a vehicle in front. The autonomous vehicle is able to drive off. I'll let this run in the background, and if you haven't asked yourself this yet, ask yourself now. How accurate are these simulations? A few minutes ago, I said simulations are absolutely crucial to pulling off testing of autonomous vehicles. But we need to make sure that the simulations themselves are accurate. We're using models to represent the environment, computational models to represent the environment where these autonomous vehicle simulations are taking place. We're also using models to simulate the sensors and the perceptions and the signal processing that's going on behind the scenes. If those models are not accurate, then all of this falls apart. Okay? We get no value out of it. In fact, it's probably detrimental. All right? So we really need to make sure that the models we're using in the simulations are as accurate as they can be. So this then lets me get into simulation of the environment and simulation of the sensory and the perception systems inside of autonomous vehicles. So it's not just simulating the whole vehicle, it's also being able to simulate the components, to generate the models, to allow us to simulate the whole vehicle to deliver autonomous vehicles in a reasonable time frame. I'm going to start a video clip here. The video on the left is an environment which is generated using traditional rendering. And by traditional rendering, what I mean is the lighting, it's sort of midday, and it's pretty easy to do. What you do is, kind of add some extra gray or, turn down the brightness in certain areas. And it looks pretty accurate, looks pretty good. The problem is, pretty good is oftentimes not good enough. And when we're talking about our safety and using simulation, we really want it to be a lot better. The video on the right, which is taken at, it runs through simultaneously. The video on the right is at a little bit more difficult time of day, either dawn or dusk, where there can be a lot of weird lighting, there can be reflections, etc. And in this case, being able to simulate the light, not just come up with graphic effects that make it look realistic, but here we're actually simulating the source of light, the sun in the background, the reflections coming off of the building windows, the contrast that exists as this light shines through small gaps in the environment, the material properties themselves of the road, of the glass, of the structures. The light reflects and interacts with all of those materials. And we need to capture that to come up with very accurate representations of the environment. I'll up the stakes a little bit here, right? Driving on a highway, midday, dawn, dusk, no other cars on the road, no pedestrians, not so hard. But what happens if we get into an urban environment? I'm going to run this clip, so it's the same kind of thing, more traditional rendering on the left-hand side and proper light simulation on the right-hand side. I'll run this clip twice. The first time, what I would like you to do, especially if you're a driver, look for the things that might trip you up, especially on the right-hand side, right? That simulated light propagation is going to hopefully show you the things that you might recognize as having caused problems for you as a driver. I'll run the clip through again at the end, a second time, and highlight those things for you. So the video is about to reset. What I would like you to do is realize the traffic light. I had a really hard time seeing what color the traffic light was. In fact, I didn't even see the traffic light till it kind of came out from where the sun was really glaring behind it. If we don't simulate the environment properly, there's no way we're going to be able to test our autonomous vehicle simulation environment to make sure we can pick up on those things. So we drive a little bit further ahead. Notice on the left-hand side, that white car in front, it's pretty easy to see, even with the shadows. But on the right-hand side, because of the contrast, not so easy. And this fellow running out in front of us, it was really difficult to see. It was because of the backlighting that came about with the sun there. We need to do proper environment simulation, proper real light simulation with all of the features of the environment in place to make the most of this part of simulation. The next piece that I'll focus on is what happens when we want to introduce simulation in terms of the sensor design and the perception and the modeling that goes into that as part of overall autonomous vehicle simulation. This is very much a repeat of the slide that I presented earlier. It's just a reminder, we're talking about LiDAR and radar, detection and ranging systems, camera systems, and then the electronics that bind it all together. What I decided to do to help you understand a little bit more about engineering simulation is to give you a couple of live demos, some short live demos. The really important thing here is to understand exactly what users of simulation understand. It's about discovering things you didn't know before. Okay? So let's switch over. So I've got my simulation software running in the background, and I'm going to choose to simulate this bracket. Now, I'm sure you guys are familiar with this idea of a bracket. On the left-hand side, there are two mounting points, so top and bottom on the left-hand side. And on the right-hand side, we have a load. That's this arrow pulling down. And we're interested in seeing perhaps what happens when we pull down on this bracket. Now, the load that's there is 200 newtons, and depending on how hefty that bracket is, it's not going to deform very much. 200 newtons, for what, you know, an idea, it's 200 apples. It's a fairly significant load. But let's increase that load. As you know, while this thing is running, let's increase that load 2 orders of magnitude. And now we see we're really pulling here. Okay? Now, is this relevant in the autonomous vehicle context? Yeah, the vehicle itself has all kinds of structural components like this, mounting all of the electronics, mounting the various pieces, the new pieces on the vehicle. We need to be able to see whether these things are going to last, whether they're going to deform, whether there's going to be physical interference between the pieces. A really interesting thing, and I mentioned discovery before, is that if you think about it, if we apply this load straight down on the end of this bracket, I would think naturally that it should deform straight down. So I'll show you here. Let's look at it end on. Okay, we're looking straight down the bracket here, and you see that arrow pulling straight down. But the bracket's not deforming straight down. It's actually pulling off to the side. I'm pulling straight down, and the bracket is actually deforming off to the side. We just discovered something that we didn't know before. And then as we look at the simulation and the results, we can see, oh, it's because of this asymmetry down here in the bracket itself. I don't know why that's there. Maybe it was there to allow this bracket to fit around or beside some bolt or some nut. But that asymmetry in the actual design is going to introduce something that might not be so intuitive. That's what simulation is useful for. Let's look at another example which is also relevant in the context of autonomous vehicles. This is a heat sink. Essentially what happens with heat sinks, why do we use them? It's to get rid of heat. So we've got a lot of electronics components. Okay, we've got a lot of chips that are on circuit boards. Those chips go through tremendous amounts of electricity. They get hot. If they get hot, they fail. We need to keep them cool. We can blow air past them, or what we can do is increase their surface area and blow air past them to help keep them cool. So what happens is that we create heat sinks like this out of a thermally conductive material, like a metal, and we glue them or strap them on top of a chip. So this part, this bottom pad, would be glued on top of a chip. And as that chip heats up, we're going to see the temperature distribution, and that's what's shown in colors here. We're going to see the temperature hottest, where that contact is made, and where the fins are and where air is blowing past, we'll see the temperature is the coolest. The temperature, maximum temperature, which is on the, down here, I don't know if you can see it. I'll tell you what it is. It's about 72 degrees Celsius. And now what I want to do is some discovery. So what happens if I change the number of fins from left to right and increase them? I get more surface area. Hopefully the temperature should go down. So let's add one more fin. There it is. Now the simulation is running again, and what we're hoping to see is that there's not quite as much red. The temperatures drop down, and indeed, if I look on the right, the temperature dropped from 72 degrees down to about 65 degrees. It's good. That was a good design change. Another alternative would be to say, let's start at the beginning again and increase the area where the heat transfer can take place by grabbing the top of one of these and pulling it out. Let's make these fins longer. And if we do that, again, what we're hoping is that we don't end up with 72 degrees. We hope that we end up with something less. So more blue, less red. We're down at 63 degrees. This is what engineers use simulation software for. It's to do what-if analysis. It's to do discovery. The next thing that I'd like to do is, these are good outcomes. It's equally important, perhaps more important, to look at bad outcomes. I mentioned before that we might strap one of these heat sinks on top of a chip. We're blowing air past it with fans. Why do we have to do that incidentally? Because we're introducing all of these electronics components in cars. Cars are in the rain, in the slush, in the dirt, in the oil. You can't have these chips and fins and everything hanging out in the open. They'll eventually fail because of that. So you put them in containers, seal them in. Well, you don't get a lot of cooling in these closed containers, generally speaking. So you have to introduce fans and heat sinks to circulate the air and cool things down. Well, what would happen if we had a failure of the fan? So this value here is how strong the blowing is, how strong the fan is. Let's say we lost only 10% of the cooling capabilities. The temperature is no longer 72 degrees. Here we are. It's another 5 degrees hotter. I don't know. Maybe 75 degrees was a magic number where bad things happen. Here we're at 77 degrees. Maybe it's still okay. Maybe it's not. That's if we lost 10% of the cooling capabilities. If the fan went off, if there was no longer blowing, we're in a situation where there's something called natural convection at best that happens. And that's just air, getting really hot and circulating around. And so let's say we lost 90% of the cooling. It's red, all red. Bad things are happening. That number is climbing. If you can read it, we're just under 500 degrees Celsius. Okay? This electronics device is toast, literally toast. All right? These are the kinds of things that we want to find out long before we ever have autonomous vehicles driving around in a widespread way. We want to know whether they're going to work or not work. Okay, so I introduced the idea of the various electronics components, the various sensors that need to come into play. We talked about needing good models of them to introduce into our overall autonomous vehicle simulation. But what about the actual design of the components? If we can design them well and use simulation there, we can actually get good models out of those simulations to feed the full autonomous vehicle simulations. So let's take a look at, for example, how the simulations that I just showed you could fit in and be useful in the context of designing any one of these components. I'll start with LiDAR. So what happens with LiDAR design is that we first take a look at how the light signal, how the laser signal is being projected out into the environment. We want to make sure that that signal is very clean and very predictable, right? We're firing a laser, we're scanning left to right, top to bottom, okay? And we want a very, very nice, predictable signal going out. So there's the scan pattern, and I would say it's very predictable, okay? If it was some random set of points, we're not going to be able to take a lot from it. Once the light is reflected back, we actually have to have a receiver that receives that light. And if the signal going out was a mess, you're not going to make sense of what's coming back, all right? So here we are with the simulation on the return trip on the receiver side. We're able to simulate that as well and get a good design of the optics, of the actual emitter, of the actual receiver itself, of the housing that contains all of it. Once we have the component, once we have the LiDAR itself, we want to introduce it into the autonomous vehicle itself. We want to do it with a balance of form and function. Of course, form means we don't want these things strapped on, as I showed you in the earlier slide. We want them hidden away in the vehicle in a pleasing way. But from a functional perspective, there are trade-offs to be made, and it's a balance of the two. So what's happening as I run through this analysis is we've got a LiDAR placed inside of a headlight, and as we move the LiDAR from the front of the headlight, very close to the outside, further back, the field of view, that's that yellow ray pattern, the field of view changes. And here you can actually see on the right-hand side what it actually sees from the environment. There's a wall on the left side. There's something off in the distance, some light posts shown in light blue there. But as we move that light fore and aft, that LiDAR fore and aft, we're getting good feedback in terms of what that balance of form and function are. Maybe it doesn't matter, maybe it does matter in terms of where it's ultimately placed, in terms of how pleasing it is. We could take the LiDAR, and instead of putting it up by the headlights, we could put it up by the rear view mirror. So here we have an emitter and a receiver, and we're just tipping the LiDAR up and down, the emitter up and down, and we're seeing how far can we see, and what happens when we tip it down? Well, there's interference from the actual housing that is around the LiDAR. So what do? Do we change the position of the LiDAR? Do we change the housing, maybe flare it out a little bit? These are the design decisions that we can make after discovering this. There are a lot of corner cases that are going to come up, a lot of things we weren't expecting. From a LiDAR perspective, remember this is light that's being fired out. These are laser lights that are being fired out from some emitter, and so there's the scan pattern, and that light is bouncing off of the various things that are out in front. And here's the return signal, which has been processed. On the top, we see what happens if the vehicle directly in front of us is painted white. All the light is reflected back. An interesting thing happens if you paint that car black. It disappears. Good thing we found out about that in the simulation. What can we do about it? Well, the good thing is we can change the pigments in the paint, right? And by doing so, we can actually get the return signal. We could change the frequencies at which the LiDAR is, the laser frequencies. That might help, might not help. Maybe we do have to change the paint. Maybe we don't have to change the paint. But at least we know what we're not going to see if we proceed without having a test like this. Radar works in a similar way. Here, we have the ability to design radar antenna arrays. Okay, so that plate in the background, that's actually an example of a radar antenna array. And what it's doing, again, is sending out radio signals. And the pattern that you see, that lobed pattern, essentially what it's doing is it's showing you the relative strength, so that's how big or how long those things are in the coloring, and then also the various directions that have strong signals sent out. And so by changing the antenna array, we can actually change the radar signal and customize it for various applications. If, for example, we integrate that radar antenna into a bumper for something like parking assist, maybe we want a flatter signal, right? We're not trying to see objects far away, we're trying to see objects close by. The balance of form and function come into play again here. If we mount that radar antenna on the outside in plain view with no obstructions in front of it, fantastic. That is the signal it's going to send out, and we'll be able to do a good job of processing the signal that comes back. The problem is that I wouldn't want a big radar antenna array hanging off the front of my car. Instead, I'd want it hidden in the bumper. There's a big problem with that, because if you put a bumper in front of the radar antenna, this is the signal that goes out. It's a lot messier than the other signal that I had shown you before. If it's messier on the way out, the return signal is going to be messier. We just made our lives a lot harder in terms of being able to detect what that radar signal, the return signal is, and our processing afterwards got a lot harder. So being able to simulate not just how we need to design the radar antenna to get the distribution and intensities that we want, we need to be able to simulate what happens when we put that behind a bumper, what happens to the signal, and then we need to be able to use all of that information in designing the receivers and what happens downstream of that. How is radar used? Here's an example simulation of an environment, a driving environment, with various vehicles driving around. We've got circled down at the bottom the vehicle that's sending out the radar pulses, and on the bottom right, we've got the actual rays that are being shot and reflected. Okay, so you can imagine that these are waves that are going in various directions and bouncing and coming back. What does the car see? What does the autonomous vehicle see? It sees something like what's shown on the left-hand side. The axes in this graph, so from bottom to top, is how far away objects are. And by the way, the colored blips on there, those are the things that are being seen. The things that are closest to our car of interest, they're the things that are at the bottom. So most of the stuff that we are seeing is very close to us, somewhere between 20 and 40 meters away from us. Objects that are moving away from the autonomous vehicle, they're on the left-hand side. So if there are some of these vehicles that are moving faster than our car, they'll be moving away. Those ones will be on the left-hand side. If there are vehicles moving towards us, these guys, they'll be on the right-hand side. And things that are going slower will be closer to the center. Things that are going faster relative to our vehicle, they're out to the sides. So what are some of those things? Let's start interpreting this, because that's what our vehicle is going to have to do. We have to teach our vehicles to do this. Well, you see that vertical line of signals. All of those things are moving at about 10 meters per second toward the vehicle. And they're varying distances away. Those things are probably the street lights. And it's probably telling us that we're moving at about 10 meters per second relative to them. The first and really dominant blip that we see is that white car that's right in front of us. What we see is that it's on the left-hand side, so it's moving away from us. It's going a little faster than we are, and it's very close to us. It's at the bottom of the screen. That pink truck is actually further away from us. The radar is confirming that, and because it's more off to the left, we see that it's actually going significantly faster than we are. So we should expect that it's going to pull away when I run the animation. The blue truck, we see it on the right-hand side. Notice that that signal is not very strong. And the reason why that signal is not very strong is because it's partially obstructed by the pink truck. So as we're designing these radar systems and these signal processing pieces of software, we need to learn that that's what's going to happen. We need to take all of that into consideration. Finally, the last thing that I'll highlight, and this is the one that I want you to watch because that's where we get into some interesting edge case situations, is this brown vehicle. This brown vehicle is way off in the distance, a fairly faint blip. We see it's, close to 90 meters away from us, and it's coming towards us rather quickly at about 40 meters per second. And here, if I run that animation, I want you to watch that blip. That was the vehicle, that brown vehicle right here. And the interesting thing is as it tucks behind that blue truck, look what happens to it. It disappears. So This is helping us to understand the kinds of things that we need to watch out for. When is radar going to be helpful? When is radar not going to be helpful? Do we need to understand what kind of object that is and make a record of it? Because if it disappears, where did it go? It's not that it truly just disappeared. It's still there, but we're not tracking it with this particular system. I mentioned before we can use simulation in the design of cameras, and I'd like to walk through that as well. In this simulation software, we're going through and selecting different kinds of lens elements, different shapes, different materials. We're stacking them so that we get the right optical behavior. We're mounting it inside of a camera housing itself. Then we go on to test what actually happens as we have different light signals propagating through the actual camera hardware. So we have some upstream signal, and what we're interested then in doing is watching what happens to that signal from the outside world as it runs through the actual lens system and onto the receiver, onto the element at the back. Things that we're checking for: overall sensitivity, noise reduction or amplification. You know that if you have a digital camera or any camera, if you take certain kinds of photos with a poor quality lens, you don't get very good outcomes. So this helps us to design what kinds of camera systems we actually want and need. Once we have the camera designed, the next step is to say, let's put it on top of a car in a certain way. So here we've mounted it on top of a car. The intention is to do a simulation and do an assessment of what is it that each camera sees, and are there any blind spots. The camera in front sees this image. Front left, we had a camera at the front left, is this. Front right, down here. Back left is up here. Back right, down here. This is the interesting thing. The orange rays show us where we actually have good coverage with the cameras. We can see well there. The part that we can't see is black. We have no idea what's going on behind us, but more importantly, we have no idea what's going on over our shoulder to the left and over our shoulder to the right, and perhaps what's going on really close to the vehicle in front. This is blind spot. This is exactly the kind of thing that we have to worry about as we drive. So by introducing cameras and models of cameras and doing simulations, we can understand what the actual blind spots are going to be in real autonomous vehicle applications. I mentioned before, if we made perhaps a poor selection of optical components in our cameras, we might not get a very good outcome. This is something you saw earlier. If we had selected particularly poor optical components, it's conceivable that this glare would have become so significant that we would not have been able to actually see the colors, or even perhaps the signal light itself, for a long period of time. We need optical components that allow us to be able to see different things very well, even with difficult visual environments. Starting to get to the end here, all of these pieces have a lot of electronics components to tie them all together. We do a lot of simulation, or allow for a lot of simulation on the electrical systems themselves. Here's a printed circuit board. There are a lot of chips on that printed circuit board. There's a path through the circuit that's highlighted in red with some green around it. What kinds of things are we simulating for that path? Well, those things have various signals going through, right? Pulses of electricity going through. We need to ensure that the fidelity of those signals are maintained, or is maintained, as the signal propagates through the wire path, or through the trace itself. There's a certain amount of power that needs to be maintained through the signal as well, or as part of the signal. We need to be able to assess whether that power is attenuated or drops off because of the path through the various traces on the circuit board. Electromigration is another really insidious thing. It was great. I got to learn about this as part of preparing. But electromigration happens when you fire electrons through these paths, and they hit atoms of the metal. They actually scatter. The momentum of the electrons scatters out the metal. And what ends up happening is you can introduce short circuits, or you can introduce open circuits because of that. which is particularly detrimental if you've got a system that depends very much on these various electrical signals. All of these systems are running at a low voltage, and if there's electrostatic discharge, it becomes really important that we're not frying these electrical components that are running at such a low voltage. The last thing is we've got a lot of electrical components that are talking, and they can be talking to each other in inadvertent ways. So electromagnetic emissions are particularly important as well. All of these things are exacerbated using thermal effects, or because of thermal effects. I mentioned cooling as a really important piece of the puzzle. We need to keep that in mind, and simulation is critically important for that. Not to mention the vibration that goes on as we're driving this vehicle through town. All of those vibrations can have structural effects on the circuit boards themselves. It can lead to failures in that context as well. I started the talk saying that simulation was a critical piece of developing autonomous vehicles. The truth is, it's not just simulation. I want you to walk away from this, whenever someone says simulation is important, simulation is fantastic, ask the question, how accurate is it? It's actually physically accurate simulation that's critically important. Global car makers have already factored in simulation in their plans for the development of autonomous vehicles. And in doing some research, I came up with feedback from the 11 largest automakers in terms of when they think autonomous vehicles will be available. Clearly, we missed the mark on 2017 and 2018 to a large extent, but that 10-year mark, that's the latest time that any of these automobile manufacturers has come up with, 2030. Let's go back here, back to the very beginning. Autonomous vehicles are going to have a profound impact on our lives. There's no question about it. That revolution has begun. These are the kinds of things that we can both look forward to and the things that we need to be aware of. There's no way we're going to pull off all of the testing that's needed in order to assure ourselves that they're safe. In order to do that, we need something other than basic road testing. We need simulation. And with simulation, we can do this in a matter of a decade or a few decades worth of time. And again, fundamentally, it's not just simulation. It's physically accurate simulation that's critically important in this adventure. That's it. Thank you.
Thank you very much, Steve. That was really thought-provoking. I'm sure that there are questions from the audience. So what we're going to do is use the catch box. So if you have a question, just raise your hand and we'll get to you with the microphone so that not only people here can hear the question, but also those on the live stream. So let's start over here.
Hi, thanks for the interesting presentation. So my question was, when you simulate things, you may not be able to come up with those unknown unknowns, right? Things that haven't been seen. And let's say we'll make, say, deep learning or AI to deal with those cases. But even for those, when you use deep learning, say, the training data cannot be gleaned from the simulations because that is not independent data. So in order to properly learn about these unknown unknowns, you have to get the data from the real world. You cannot get it from simulations and their data. So in this timeline that you were saying that we could do most of the 8 billion miles with simulations, how much of real driving will we have to do anyway?
Yeah, the short answer to that is I don't know. There's no question that simulation is a really important piece of the puzzle, right? That will help us to cover a tremendous amount of ground. But we began with real driving and real testing. That has to continue. There's no question that has to continue. So I don't think it certainly isn't an either-or thing. What percentage will be with real vehicles, that I don't know. You know, what I have seen, there was an article that was published yesterday by the CBC, is that the Ontario government, I mentioned it at the beginning of the talk as well, the Ontario government is saying we want autonomous vehicles to be on our roadways so that we can be doing testing. And so there's a commitment not to reduce the amount of real vehicle testing, but also to have that ramp up as well, I'm sure. Yeah.
Thank you very much. That was really, really interesting. I'm curious as to your simulations, how complicated some of the simulations you've done or they've started to use. Because I'm saying I'm looking at a day out here, like today on the roads, and obviously the case you gave, although complex, was quite simple in comparison today. I'd be curious to see how far down that road they've taken it, because I've heard some reports saying that we may never have autonomous vehicles running in Canada in the wintertime because it's just too many variables.
Okay, I mean, that's a really good question. I think the thing to keep in mind here is it goes back to how accurate are the physics that are going into the models. And to me, I think the way it will end up being is that as long as we can push the accuracy to be like what we see outside, we will be able to use simulation and be able to explore these kinds of environments. Now, that's not to say that after we've done the simulation, we may still conclude autonomous vehicles are not viable in these systems, right? Just being able to do the simulation won't magically tell you you're okay to do it. You still have to have control systems that are going to be able to handle these kinds of situations. But the simulations that we are now able to do have again, by looking at how light is propagated, how we're sensing things, we'll be able to determine through simulation that, yeah, autonomous vehicles are not good on days like this.
Hello.
Hi.
First of all, that was a very lovely set of slides and how you presented that, so I want to just comment on that before I ask my question, so thank you for that. The one thing that, you know, in my sort of armchair interest of this field seems to be that we have the autonomous vehicles themselves, just like individual humans that look around, we perceive our environment and make decisions based on that. But there's also the whole network of cars layer, which now introduces certain benefits to that, as well as integration of other technologies in like smart cities, smart highways, that sort of thing. I'm sort of curious if you have any comments on how those different layers will come together, or what at least you're seeing out there. Is that something that's likely to impact us in the short term and make progress faster, or does it seem like a far-off thing?
So again, that one I'm going to have to defer. That's not something that I'm familiar with. I think, you know, again, the more information that's available, it stands to reason. The more information that's available, the better off these autonomous systems can be. If I take it back to the topic that I was presenting, which is simulation, I would say that those things would become part of the environment simulation. And so ultimately what we would like to do is, as those kinds of environmental systems come online, we integrate those into the overall simulation process and, again, be able to test with greater fidelity what the autonomous vehicles are going to do in those environments.
Imagine they've got their own simulation stacks on top of that as well.
Absolutely, yes, yes.
Very meta simulation.
Yep.
When you run these simulations, do you take account into like ethical concerns? So for example, if there's 3 lanes and two of them go straight and the right lane is only a right turn lane, or would a car like take the right turn lane to avoid the traffic in the other 2 lanes and just cut back into that lane?
So,
Because it's faster, right?
yeah, so that's more a question for the people that are doing the simulation and the people that are setting up the simulation environment. As well, it's a question for the people that are programming the control systems. I did a good job, I think, in letting you know what kinds of systems and simulations are in play here, because you're coming back and saying, okay, yeah, but what if you do simulation of this? You know, who's responsible for those decisions? And even the fact that those decisions need to be made is a really important piece. And we can start to see that as we gain more familiarity with autonomous vehicles and doing simulations. You know, from an ethical perspective, again, it goes back to the people that are programming the control systems. They're the ones that have to make the decisions. The intention for me today, by the way, was really just to touch upon how simulation can be used to assess situations like that for autonomous vehicles.
Great. We have one question online, so I'm just going to read it out, and hopefully you can answer it. So this is from Bazad. He's asking, I'm wondering about connection to control design tools and Modelica models and machine learning tools. And by connection, I mean software interference so that one can build their control or machine learning algorithm in Python or other environments and test it in this simulation environment.
Okay, so that's a fairly specific set of questions.
Also importing models made using Modelica.
Okay, so those are very specific questions in terms of, for example, the software that ANSYS or other providers provides. Okay, I put up the slide that showed the software, and there was a window there that showed how the control system can be defined, and that piece of software does interface with software in the outside world, where pieces like what you've talked about could be integrated into that environment. But the specific list of third-party software that can be integrated, I don't know what they are. What I would invite the person asking the question to do is visit ANSYS, for example, ansys.com, and start looking into the various pieces of software that are available and what they might be able to do in terms of interfacing with the software you're interested in.
Thank you so much again, Steve. That was our last question. I'm sorry we're out of time, so I am going to have to cut it off. Hopefully Steve can stay with us a few more minutes. Afterwards, if you're here in person, feel free to come up and speak with Steve. But again, we just want to say thank you for coming. It was an awesome presentation.
Thank you as well for the opportunity.
Just in wrapping up, I want to mention that we have another couple of sessions coming up in the future. They're not on Eventbrite yet, but they will be very shortly. On February 20th, we're going to be talking about another new, or some more new opportunities that we have available. And so this one's going to be about commercializing your tech solutions through CENGEN project. CENGEN is a Center for Excellence in Next Generation Networking. So that presents a lot of opportunities for your business as well. So please come out and be part of that talk. And then on March 13th, we have a speaker that's going to be with us from CIBC, and they're going to speak about vector embedding. So watch for those two sessions coming up shortly on the Communitech website and on Eventbrite. Thanks for coming out.